Hello everyone, in this video we will be making a Metalens using the PlanOpSim software based on the far field intensity that we specify using a series of nanostructures. So contrary to the previous example where we were looking at near fields, now we're going to have something a little bit more involved and directly specify the far field wavefront, far field intensity that we want to reproduce using. We start off by defining a new component here under dioxide lenses, which I will call far field component. Add that. And I have to start here in the component tab by specifying the dimensions that I want to use and the series of nanostructures, the family that I want to desired for. Start by the dimensions. I'll again a small one of 250 by 250 microns. And for the family, I will select same TiO2 structures. I'll use all 4 of them to our group of selected family members and save that. So now we've defined a component. It's going to be 250 by 250 microns in size, and it will use 4 titanium dioxide nanopillars. Next step is to define target far field. We'll go here. Currently we don't have any design target yet, so we go ahead and add one here with the plus button. It's a new design target. I will start editing. The first step is the same as when using a near field. Set both the exit light conditions as the incident light conditions. That's called the set point. We give this name. This is my far field target. I'm interested in the 0,0 diffraction order for transmitted light, EE polarization, and I want to optimize, reproduce both the phase and amplitude. Select complex. For my set point, I will choose normal incidence, so both angles 0, and the wavelength set to 600 nanometer. Okay with that and save. And then we go down bottom of the screen where we have the definition of the far field wavefront right on the left of the near field wavefront. So in this case, we're specifying a far field. We'll edit the far field. Note that you cannot simultaneously set a near field and a far field because that would create a conflicting requirement within the design. So as a far field target, we will not set none. Create a new one. Window here where we can define that target. So FF target. Can give it a description. The center coordinates, I will pick them to be the same in X and Y as our MetaComponent, but have the projection be 1 millimeter away 1000. Orientation can all be 0. This indicates that my angles are, that my planes are actually parallel to each other. The next 2 settings, tolerance and maximum iterations, relate to the algorithm that the software uses to guess which near field it needs to reproduce and on the space of the MetaComponent in order to produce the desired far field. There's an iterative algorithm inside the software there that will iterate back and forth between the near field and the far field until either it finds that the error is sufficiently low, below the tolerance criterion, or that it is taking too long, too many iterations, exceeds the max iteration. So for this case, I will set the tolerance to 10 to the minus 8 and the maximum number of iterations to 100. The wavefront can have different dimensions than the component itself. In this case, I will choose it to be 100 by 100 microns. Save that. Now there's one thing that I have not done yet, and that is provide the actual intensity profile. This is what we will do right now. So for now I click confirm. I select my newly created wavefront far field target, be the target that I want. And I edit it once again to upload new target. This wavefront I have prepared separately as a JSON file, similar to the way you handle it in a near field wavefront. The only difference is that now we only specify the intensity, whereas in a near field wavefront we have to specify both amplitude and phase. So I'll drag my near field target into the box here, and we give it some time to upload, and there we have the far field target that I specified. So I've chosen an elliptical shaped Gaussian, which is a bit narrower in the X direction and a bit wider in the Y direction. We now have everything regarding to our target. And store that. It's saved. Voila. With this we have defined the target. We previously defined also the shape of the component. We're now ready to start our design. The far field target design takes an additional step compared to a near field target design, because it first has to estimate what will be the right near field that produces the far field that we specified. And then afterwards, we'll use that near field and reproduce it using the family, the structures selected to produce that out of the incident light field. So where before we had specified near field one step, we're replicating using structures, we now have a two-step optimization where first we take the intensity, figure out for our wavelength and what should be the near field. This is done using the algorithm. When that has concluded, we have a near field which we can then use to reproduce using our family of structures. You won't notice anything, but this is what's happening under the hood. So what we do now is we start the design and let the optimizer run until it has found a solution. There we go. So the design is now queued, and we'll see it progress one by one until we have it working. So let's pause the video for a bit here. And there we go. After a couple of minutes, the design is done, and we can have a look on the one hand PDF report. Download it here. There we have it. Report showing which components were used, which family was used, and so on. And on the other hand, we can also generate GDS mask here. Download it. Let's look at it while it's downloading. Go. We have the GDS mask. Let's open that in K-layout. And here we have the GDS design of a mask of our design. We have a 250 by area consisting of a number of layers corresponding to each of the we have. We can zoom in closer. You see there an irregular shape that's caused actually by the iterative algorithm that does not always produce a perfectly symmetrical wavefront, but instead tries to approximate the far field as best as possible. This can sometimes lead to things like optical vortices and also an irregular pattern in the GDS mask. Like this, we have a GDS file of a MetaComponent that will approximate the far field that we put in as a target. And that's how you make a far field target design using the PlanOpSim software.